These final four images have a lot of information on them and are initially a little bit difficult for students because they do use multiple levels of representation. However, with some simple explanations, I believe these images are appropriate for my students because all of my students are quickly able to recreate the charts from memory and explain the importance of the charts as they relate to diving. To help make these charts appropriate for my students, the first thing I have to consider is order. As mentioned earlier, they progress from the least complex to the most complex. So it's important that I present the charts in a sequential order. Let's look at each table or chart individually. The first and most simple image shows a diver at 165 feet of salt water. It shows the surface of the water and shows what happens in 33 feet intervals. The reason for the 33 feet intervals is that the entire atmosphere places a pressure of 14.7 pounds per square inch of pressure on the body or anything else. We call that an atmosphere. Because of the density and the weight of water, every 33 feet of water also puts an additional 14.7 pounds per square inch on each inch of the diver's body. So 33 feet of salt water is equivalent to the same amount of pressure as the entire atmosphere. So basically this chart simply shows that for every 33 feet, you're under an additional atmosphere of pressure. It also shows what would happen to the size of a gas bubble, how it would start at 100% and gradually get smaller. From this first image, students might not see the exact relationship of how much smaller the bubble is getting with each atmosphere. At that point, I go on ahead and I introduce the second table. With the second table, we actually use the Boyle's Law formula and work some problems. We start at the surface of the water with one atmosphere being pressure 1 and 1 cubic foot or whatever other unit of volume you want to use being volume 1. So we say if you double the pressure, what would happen to the volume? And I have my students solve that math problem and they realize that it would be half the volume. We do the same thing again. If the pressure starts at 1 and we increase it to 3 atmospheres, students use the formula and see that the volume would be 1/3. So basically this chart simply adds a little bit more understanding about the relationship between the pressure and the volume. You'll also notice that this chart is in meters. So I talked to the students about the difference in using meters and feet when calculating Boyle's Law with scuba diving. The third table adds density. Basically, it shows what happens to the molecules inside of a balloon or a non-rigid closed container. And what the students see is that as the balloon shrinks, the amount of molecules stay the same, so they become much more dense inside the balloon. When I show this table, I also draw to the side a scuba tank, and I show how the air inside the tank compresses. Even though the tank itself doesn't get smaller like the balloon, the air inside still compresses, so the density of the air in the balloon is greater. It's much more dense. In the fourth image, we add another component, which we mentioned earlier, which are the last two columns. In these columns, just like before, it shows the depth, the pressure, what would happen to the volume, and it shows from 6 liters that half of that would be 3. A third of the original 6 liters would be 2 liters. A fourth would be 1.5. So it shows exactly what all the previous charts have shown, but then it adds on what would happen if a diver were to basically inhale 3 liters of air into the lungs at a depth of 30 meters with 4 atmospheres of pressure. Basically what it's showing is that this relationship still holds true, that the bottom slide represents 1/4. As the diver ascends to 20 meters, it would be a third of what it would be at the surface, a half, and then all the way to 12 liters, which again would burst the lungs. So it helps them understand not only what happens to the balloon, but we also start talking about the physiology. So although this initial image is very basic and lacks a lot of detail, the final image is much more complex and has a great deal more to discuss and point out to the students so that they understand what's happening and they don't develop misconceptions. When all of these images are used in conjunction with each other, students develop the building blocks they need to synthesize all of the information about Boyle's Law, how it applies to scuba diving, and how it can affect the health and safety of a diver. So in this presentation, we've looked at how visual representations can be used to help teach Boyle's Law through scuba diving. We've seen how Boyle's Law can show different concepts of scale. We've seen different types and levels of representations, examples of horizontal and vertical translations, and we've talked about the reasons that you would use multiple representations of the same concept. We've also considered the scientific accuracy of the representations we're used, and finally, the learner and whether or not the images are appropriate for the learner and the type of things that the learner might struggle with. Altogether, we've learned that well-chosen and thoroughly explained images can help students gain conceptual and abstract understandings of difficult concepts. I find visual representations are an excellent way to help my young learners explore gas laws through the exciting sport of scuba diving, which is very safe if and only if you understand and correctly apply gas laws.